So welcome to our 6th lecture video for engineering mechanics statics. For this lecture video, we will discuss about vector multiplication. This topic is a prerequisite of our next lectures on the application of engineering mechanics, which is about moment of a force about a point and moment of a force about an axis. So we will apply this concept of vector multiplication to solve those types of problems. So for vector multiplication, we have three basic operations in performing vector multiplication, which is it will be in different uses and different approach. So we have the first one is the dot product or the scalar multiplication of vectors. Then we have the cross product, which is the vector multiplication vector approach. Then we have the scalar triple product, which is the combination of dot and cross product. So let's start first with the dot product, also referred to as the scalar product. So it can be performed between two vectors, say vectors A and B, with an angle of theta between their positive directions. So the formula, general formula, is that the vector form of A, vector notation of A, and dot product, the vector notation of B, is equals to the product of the magnitudes of A and B times cosine the angle between them. So that is the general formula. So if we draw that, it will look like this. So if this is vector A, which is this one, then we have vector B, which is this one. Then theta there is the angle measured from the positive direction of the two vectors, where A and B here is the magnitudes of the two vectors. So also take note that the angle theta, which is the angle between the two vectors, must be in between 0 to 180 degrees. The dot product is positive. The answer of this one is positive if theta is less than 90, because cosine of an angle less than 90 between 0 to 90 is positive. Then it is negative if theta is greater than 90, because cosine of an angle greater than 90 in between 90 to 180 is negative. And 0 if angle theta is 90 degrees, because cosine of 90 is 0. So this function will also be equal to 0. So these are the following important properties of dot product. So the first one is commutative property, meaning you can interchange the vectors, meaning you can perform dot product even though you interchange the two vectors. Next is distributive property. So you can do distribution of dot product if there are vectors that are in a parenthesis and added to each other. Next, since if we follow the concept of the coordinate axis, if this is I, this is J, and this is K, such that this is X, Y, and Z. So remember that the angle between them, the coordinate axis, are 90 degrees. So as I said earlier, if theta is equals to 90 degrees, the dot product is 0. So remember that angle between I and J, which is the X and Y axis, are 90 degrees. So the answer will be 0. Same goes by with J and K, which is the angle between them is also 90 degrees, which is this one, 90 degrees, J and K, and also K and I. So that is if we follow the coordinate axis XYZ axis. So the answer will be 0. That's the basic concept. And we have subsequently if theta equals 0, such that if we apply that product, example I, so of course I is the same, it is always on the x-axis. So if we apply that product in two i's, the answer is 1, because cosine of 0 is 1. Cosine of 0 is 1 if you try to calculate it. So same goes with j and k, because the angle between them is 0. I and I is parallel to each other, so there are no angle between them. So meaning it is a 0. Number 5, if we apply those principles in number 3 and 4, if we apply this one, so if we perform this function right here, a dot b, and express a and b, of course, in vector notation, so what will happen is if we dot product ax and bx, the answer is ax bx, because I dot I is 1, as I stated here. I dot I is 1. Next is, if we apply that product here, the answer is 0, because I dot j is 0. Then we have also this one. This is also 0. I dot k is 0 because the angle between I and k is 90. So if we continue doing that, this one is also 0. This one right here is ay by, because j and j is 1. Then this one right here is 0. Then here 0 because k and k and j are 90 degrees to each other. And the last one here is az bz, because k and k is 1. So this one right here is the presentation of the dot product in terms of the rectangular components. So the formula will look like this. So this is equal to AB cosine theta if we substitute this one to this one. So that will be the formula of A of the two vectors performing dot product. So it is easy to remember because you just multiply the x, y, and z components. You multiply it to each other. Then you sum it up. You add all the vectors. Then, using the same concept of dot product, we can calculate theta using the unit vectors, because if we interchange this formula, we can get this formula. If we transfer AB here in the bottom side, transpose it, then you will get this function. And remember, this one is unit vector of A dot unit vector of B. So you will get theta equals arc cos unit vector of A dot unit vector of B. So meaning you just perform dot products to the unit vector. And to perform that product, you just use this formula. So what will happen is this one will become lambda x plus lambda y and plus lambda z. So that will be the formula. You just change this with the components of the unit vector in this formula. Next, we have also the rectangular or the orthogonal component of a vector in a certain direction. Example is that if we have two vectors, and let's say we have vector b, and you want to get the component of vector b, this is the component of vector b in the direction of A. So obviously, this is right triangle because it is orthogonal. So this is, from the formula, it is b cosine theta. So this is the formula. Then you transfer A here, and what will happen is it will look like this. So if we apply dot product, this one right here is the unit vector of A, which is this one. So what will happen is you just apply dot product to vector B, which is the vector that you want to get the orthogonal component, to the unit vector on the direction of where you want the direction to go, where you want the orthogonal component of vector B to get. So this is a formula that you need to remember also, because we will have also some applications to this one. So B vector B dot lambda A. So let's have some example. So given the following vectors, calculate the dot product of A and B, the orthogonal component of B in the direction of C. So for problem A, we have A dot B. For problem B, orthogonal component of B in the direction of C, so that will be B vector dot lambda C. Then we have the angle between A and C, so that is our cos of lambda A dot lambda C. So let's try to solve first the dot product of A and B. So what we will do is just you get the rectangular components of the vector A and B. So this is By and Bz. So obviously Bx is 0. Then you apply the formula, which is this one. Then you substitute it. So you get 8, 0, 4, 2, negative 2, and 6 for the values. Then you will get the answer of negative 4 pound-feet. So that's how you get the dot product of A and B. For letter B, we have the orthogonal component of B in the direction of C. So we will, of course, the formula is like this. B vector, which is we already have the value for that. Then we have unit vector of C, which we don't have yet. So let's solve for the unit vector of C, which is C vector divided by its magnitude. So we have here the unit vector of C. So we will apply dot product. So this is lambda Cx, lambda Cy, and lambda Cz. So for B vector, we have By and Bz. So if we apply this formula, so 0 for Bx, then we have lambda Cx, we have 2 for By, then we have lambda Cy, plus 6 for Bz, then we have lambda Cz. So you will get the answer of 3.714 feet. So remember that the unit vector lambda C is unitless, so what will retain is the unit of vector V, which is in feet. So that's the answer for letter B. Then for letter C, the angle between A and C. So we have here, since the formula is like this, lambda A dot lambda C, we already have the unit vector of C from the previous solution in part B. So what we need is only the unit vector of direction A. So this is the formula, the same formula, unit vector divided by its magnitude. So the unit vector is given 8i plus 4j minus 2k divided by its magnitude. So what we will get is this unit vector. Then applying that product to the components, so this is lambda ax, then we have lambda ay, and lambda az. So using that values right there, and this one, lambda cx, lambda cy, and lambda cz. So we just need to use the values, these 6 values, and applying the dot product. So this is lambda ax and lambda cx. Then we have lambda ay and lambda cy plus lambda az plus lambda times lambda cz. So if we multiply that, you'll get cosine theta of 0.162. If you perform this one, this is 0.162. Then you will get an angle of 80.7 degrees. So that is the angle between vectors A and C. So the next vector multiplication that we will discuss is the cross product, which is also referred to as the vector product. It can be performed between two vectors A and B with an angle theta between their positive direction as shown in the figure. So the formula cross AB is equals to this one. As you can see, this pattern of the A, as you can see, we have here a dot and the direction of the angle. So the dot here is the first vector A, and the arrowhead is the second vector B. Following the right hand rule, which is the curling of your fingers, as you can see, we have a right hand with a thumb directing upward and the fingers curling in this direction. So the curling of the direction of the curling of the fingers is also the same. The curling or the direction of theta from the dot to the arrowhead. And vector C right here is the direction of the thumb. So meaning, if we interchange, if we want to interchange, let's say if you want B cross A, so what will happen now is that if you follow the right hand rule, it will look like this. This is theta, B cross A. And if you use your right hand, your thumb here will point downward. So this is C, vector C. Because your fingers, your curling of your fingers is like this and your thumb is going downward. So that's how you follow the right hand rule. Meaning you will use the right hand to get the direction of vector C and determine which is the first vector and the second vector. Because the cross product is not cannot be interchanged, unlike the dot product. So note that the same as dot product, theta must be in between 0 to 180 degrees and C is always a positive number. So the following are the important properties of cross product. So C is perpendicular to A and B. So that is another important thing to remember, that the angle between C and B is 90 degrees. Same goes by with C and A. So that is 90 degrees. So that is perpendicular to both the two vectors. In the direction determined by the right hand rule, as I said earlier, which states that the direction of theta, which is, as you can see, is directed from A to B, is the same direction as your right hand fingers, which is this one, your four fingers, curled at the same time as your thumb, which is this one, pointing in the direction of C, as shown in the figure. So the cross product is distributive, can be distributed, the same as the dot product. The cross product is not associative, so meaning it cannot be interchanged, because if you interchange, what will happen is you will get the opposite direction of C, as I indicated using the right hand rule. Next is, since theta is 90 degrees, the cross product is 1. Theta equals 90 degrees because sine of 90 degrees is 1. So by definition, we can say that, so remember that I and J are 90 degrees. And following the right hand rule, it is k. So j and k, following the right hand rule, we have I. But if we interchange this one, if we get j cross I, we will get negative k. Because if we follow the coordinate axis, this is I, j, and k. If we use j and I, we will get negative k. It will look like this. So I didn't write it here. As long as if we interchange this one, k and j, example this one, k and j, so you will get negative I. That is negative I. And if you want I and k, so what will happen here if we use this one, this is the dot, this is the arrowhead, you will get negative j. So k, I dot a cross k is negative j. So that's how you interpret the scenario if you use the coordinate axis. So subsequently, if we use theta equals 0, the answer is 0 because sine of 0 is 0. So I cross I and j cross j and k cross k is 0. The exact opposite of the dot product, because dot product cosine of 0 is 1. So using the principles here in 4 and 5, we can have the formulation for cross product. So let's start with AX and BX. So we will get AXI plus BXI is, since I cross I is 0, so we don't have the value for AX and BX multiplied to each other. So next is, if we have this one here is 0, if we use this one, we will get AX by, that will be k. That is k. The next is, if we have AX and BZ, so remember that IK is negative j. So to make this faster, let's just check the formula right here, because this is more easier. As you can see, we have AX and BX, so we don't see here AX and BX connected to each other because I and I is 0. If we try AX and BY, so you will get AX BY K. So this is this one right here, AX BY K. And if we try AX and BZ, so AX BZ IK is negative J. So this one right here, negative AX BZ times J. So the same goes by with here, AY BX JI is negative K. So that is AY BX negative K. So this one also right here, J and J is 0, so we don't see AY BY here. AY BZ K, J and K, so that is AY BZ and I. So this is difficult to memorize, this one. So I don't recommend this formula to use because this is very difficult to remember. So there is an easier way to remember this formulation. So we can also get an identical expression if we, using this formula, by obtaining the determinants of a 3 by 3 matrix below. So if we perform this matrix right here, this is also the same to this one. So this one is easy to remember because if you know already how to get the determinants of a 3 by 3 matrix, like this one, so we have I, J, K, and we have the components of A and the components of B. That is very easy to remember because you just place here the vectors, let's say I, J, K, then we have components A and components of B. So that is very easy to remember. You just put the values here and perform the determinants. how do we get the determinants? You can review your mathematics in calculating the determinants of a 3x3 matrix. So we have so many methods to solve for that determinants. Okay, so let's have an example in a cross product. So we have here, given the following vector shown, calculate the cross product of A and B and the unit vector that is perpendicular to both A and B. Given, we have two vectors, A and B. And how to calculate? So first is, we have to get the cross product of A and B. So to do that, I will do the determinants of a 3x3 matrix and show you how to do it. So we have here the formula. So you just arrange I, j, k, the components of A, which is 8, 4, and -2, which is placed here. Then we have also the components of B, which is 0 for bx, 2 for by, and 6 for bz. So to do the 3x3 matrix, what we will do is we apply the basket case wherein we will apply arrows like this one. So example for this one, we have I, 4, and 6. We will try first the downward arrows. So we have I, 4, 6 is 24I. Then we have J, -2, and 0, that is 0. K, 8, and 2, that is 16K. So that is the downward. For upward, you just subtract. Then we have upward is 0, 4, and K. So that is 0, 2, -2, and I. So that is -4I. Then we have 6, 8, and J. So that is, I believe, 48 J. So that's how you perform. Then simplifying, if we write it down, it will look like this, 48J, the last one. So simplifying, combining like terms, we have 24I minus -4I, we have 28I. Then we have -48J, which is this one. Then we have positive 16K, so we don't have K here, so the answer is this one. So that's how you get the determinants. Easy to remember. Instead of memorizing this formula right here, this one, if you memorize the formula, you will get the same answer, but this is more complicated. So that is why, what I suggest is you use this. More easier, or shall we say it is no need to memorize complex equations. Just perform determinants and you will get the same answer as this one. So next one is the unit vector that is perpendicular for both A and B. So to do that, we know that if we apply the concept of, shall we say, cross product, so if we have cross vector A and vector B, then you know that this is theta. We know that the vector C, based on the presentation I presented a while ago, we know that vector C is perpendicular to both B and A. So meaning, the angle right here is 90 degrees and also this one, 90 degrees. That one, right there. So if you want to get the unit vector that is perpendicular to both A and B, we have the vector itself. The vector is C that is perpendicular to both A and B. But if you want the unit vector is the unit vector of vector C, which is lambda C. So what we will do now is to get first vector C. Then if we already get vector C, the answer will be the unit vector of C, which is lambda C. But there are two possible answers. Why? Because if this is vector A, shall we say vector B, and this is vector A, and this is the angle theta, so we know that this is vector C, which is perpendicular 90 degrees to both A and B. So we want lambda C. This unit vector going upward is perpendicular to A and B, but this vector also going downward, which is parallel to vector C also, the same line, meaning this is the same line, is also perpendicular to vector A and B. So this one is negative lambda C. So what we will do is we apply positive and negative values for the unit vector Z to get the final answer. So to do that, since the cross product A and B is perpendicular to both A and B, we can say that the unit vector of cross product A and B is also perpendicular to both A and B. So to do that, we have the cross product of A and B, which is 28i minus 48j plus 16k. So that is, this one right here is vector C. So to get the unit vector of lambda C, shall we say lambda, this is supposed to be lambda C, so let's just use lambda. So what we will get is this value. But again, we have the opposite direction of lambda, which is supposed to be, that is positive and negative. So the answer should be, since negative of lambda is also perpendicular to both A and B, therefore the final answer will be this one. So that's the principle behind why the final answer is both positive and negative. So the next or the last method in vector multiplication is the scalar triple product. So a vector multiplication involves three or more vectors is what we call the scalar triple product. So this is a combination wherein there are a cross product of two vectors, then the answer will be dot product to the third vector. So remember that cross product must always done first, because if we do cross product, the resulting answer is in vector form, then we can dot it to the third vector. Unlike if we first do the dot product, the resulting answer will be a scalar value. So you cannot cross product a vector to a scalar answer or a scalar value. So the formula will look like this. So if we perform cross product these two vectors, then dot it to the third vector, which is vector C. So performing first cross product, it will look like this. So this formula is from the previous topic, which is the cross product. So the same formula, which is the 3x3 matrix, then calculating the determinants. Then if we dot product, meaning if we multiply this one to this one, and also this one to this one, and multiply this one to this one, and the resulting answer will be like this. So as you can see, the formula is quite complicated to remember. So there is an easier way. Same with the cross product. We can perform the scalar triple product by calculating the determinants of a 3x3 matrix, which is easier to remember. So instead of memorizing this formula, which is the scalar triple product, we can use this formula, which is a 3x3 matrix, then calculating its determinant to get or to perform the scalar triple product. So it's easy to remember because the first vector will be placed here, the second one is placed here, and the third one is placed here. So performing the same procedure with the cross product. So let's have an example. So given the following vector shown, calculate the scalar triple product. So we have three vectors here. vector A, vector B, and vector C. A cross B dot C. So what will happen is, in the solution, we will arrange the vectors, the components of the vectors in this manner, such that for vector A, we have 8, 4, and negative 2. So for vector B is 0, 0 for x because there is no x component for vector B, 2 and 6, 0, 2, 6. Then we have 3, negative 2, and 4. So again, to perform the determinants, we need to copy these two rows right here to this one, so that we can get or perform the basket method. So what will happen is we multiply in this manner. So first one is we have 8 times 2 times 4, we have 64. Then we have 4 times 6 times 3, we have 72. Negative 2, 0, negative 2, so we have 0. So minus right here, and quantity 3 times 2 times negative 2 is negative 12. And we have negative 2 times 6 times 8, we have negative 96. 4 times 0 times 4, we have 0. So calculating the answer, we have 244 pound-feet squared. So that's how you calculate scalar tripole product. Performing combination of cross product and dot product. So let's have a practice problem. So I will give you, or shall we say, you can take a pause after you look at the problem. Try to solve the problem first on your own. Then you can play it back if you already have the answer. So the answer for this problem is so for the next problem, take a pause and try to solve this problem. So the answer for this problem is so I hope you learned something from this video. So I hope I helped you with your studies. So thank you for listening, watching to my video, and please don't forget to like and subscribe for more videos to come.